Hello community, so great that you're here. Today we explore how Harvard University, Google DeepMind, MIT, IBM could have here together with a PhD student in its third year at Hong Kong University, how they could develop here the next AI step, world foundation models. Yeah, AI breaks free from language. So this concept of an AI world model is not new. It is a critical element in the current reinforcement learning and in the current AI decision-making tasks that are examined here by AI research. And this breaking free from an LLM is absolutely fascinating, but we encounter a lot of problems. So let's have a look at it. Now, days ago, I showed you here NVIDIA, their latest model here, their world foundation model here, the N1 model. And we looked here, in particular, do you remember LAPA, the Latent Action Representation Space, where we had a vector quantized variational autoencoding. And I showed you in detail the encoder, the vector quantization, the decoder. We had a look at the loss function. We analyzed here the elements of the loss function. And then we had a look at flow matching, you remember? And this was the technique used to train now the diffusion transformer in N1 to generate here the actions necessary. And I told you it's about learning a time-dependent vector field. And I also showed you then in the notes here that there's a beautiful course, MIT Computer Science Class 6S184. My goodness, Generative AI with Stochastic Differential Equation. And here you have a beautiful, I think one of the best introduction to flow matching and diffusion models. And here you have 3 YouTube videos, I think more than an hour. And if you think my videos are boring, my goodness, have a look at those videos. But the material from MIT is excellent. So I showed you here website, Diffusion, CSAIL, MIT, ADU. They give you here really the mathematical foundation here to flow matching diffusion model. I also showed you we have here Python notebooks you can use immediately. It is free for you to use. They even give you here exactly an explanation what the code is doing in the next segment. So perfectly, we understood everything and we are now on the same level that we say, let's open up the next video. Now we could go with the latest documentation from today, March 24, 2025, with Shanghai AI Laboratory and go for unified world modeling here with a geometric aware function, but this is a little bit too complicated for today. I want to make it easier for us, no? However, please note that also here we have from Stanford University, University of Toronto and Vector Institute here, a new publication, March 24, 2025, and they are going now for reasoning to learn from our latent sorts. So from the sorts that are not available to the computer, where they say, we just have a lot of data, but we don't understand how humans are actually reasoning. So they are going now here, not just for the visual structures, but also in the language model, there's now this explore here, the latent sorts in a latent space. So they have here from Stanford now the idea, we have a web text here as a compressed final outcome here of a real beautiful human sort process. And the latent sorts that I want to discover contain now the important contextual knowledge and all the reasoning steps that are critical now to the data-efficient learning of our AI systems. So the AI now wants to penetrate deeper in the human thinking process, in the human learning process, because we think, yeah, we have really to learn those AI systems to think exactly like a human. And we only have on the internet, if we say copy internet, we only have the final text. And now we build AI system that try to construct here the human contextual knowledge, the hidden sorts that are not written down on the internet. So you might say, hey, that sounds easy, but what about the next step in complexity? What about we go here if we say, okay, how do we think? But we do not restrict ourselves here to language. Because we humans, we are not just thinking in a language. We have so much more. We have touch, feel, temperature, whatever, and whatever we see, what we experience, our sensory impressions. So how can we train our AI to learn from all of this? So our next gen AI will definitely develop here an understanding of the real world of humans. It will break free from just this language, these LLMs, because they will be robotic system here, maybe living real close to us. So what we do now, the next simple step is here video frames. If you have an input here, you have a video sensor, a LiDAR sensor, whatever you have, and you might say, so if you want to understand the latent sorts here in the human thinking process, then here we have so many YouTube videos. What is happening between the video frames? Can we understand the action that is taking place here from one video frame to the next video frame to the next video frame? For example, if somebody is lifting here a hand, how can an AI understand this, abstract here the action from a visual token structure and learn that this lifting exercise, this lifting action is something we can do with a lot of different objects? How can we make this system learn to learn from all our YouTube content? Now, you might say, hey, this sounds like here the latest technology, but no, unfortunately not. As I told you, we look at a particular research paper and they use a technology from 2017. I know it's a little bit disappointing, Google, here that you go back to 2017 because this is quite some years back in the historical past. But okay, we go with a variational autoencoder and we go here with a beta factor limited variational autoencoder. No? And you remember from the video I showed you at the beginning, this N1, the latest model by NVIDIA, we're real close. You could have maybe at first a look at the N1 video and then you understand this video immediately. Because we are talking about the same topic. So what NVIDIA is developing and what here Hong Kong with MIT and Harvard is developing, they are on the same track. There are just some little subtle differences, but otherwise the trend is the same. So we are looking for a latent action autoencoder. We want to understand what action is happening in the videos because we don't have here an action labeling. So we need a self-supervised method to extract here our actions from the unlabeled videos. The AI must understand, okay, now the person is lifting its right arm, and then it sees the video content and video tokens, and then it can make a relation to this. It has to learn everything. So we are looking now at a continuous latent action representation. And you remember, our last one was a vector quantized with N1, so NVIDIA went with a simpler, if you want, non-continuous. And today, if you want, the highlight of this video is we go now for a continuous latent action representation. And of course, we use here variational autoencoder because 2017 this was discovered, and it seems that we have not discovered anything else yet. Google, Harvard, okay. So we go here with this instrument. Step one is simple, no? Unlike if you go with some discrete action approaches like here N1 by NVIDIA with a vector quantized variational autoencoder methodology, this new we have now a continuous latent space, and what we do, we build here our latent action autoencoder that can extract now context invariant actions from all the different videos that are now transferable across different contexts. So this means if I have a video frame where I see that a person picks up a pencil from a table, or a person picks up a glass of water from a table, or a cup of coffee from the table, the context invariant action to pick something up from a table is now transferable by the AI across all the different contexts. A table, another surface, whatever it is. But we have to learn in the AI model that this is more or less all the same. And this is real complex. Now you might say, okay, what kind of transformer architecture are they using? Do they develop a new transformer architecture, huh? Google. Unfortunately, no. They go back here to Genie. And you know, this was here from end of February 2024. This was here a paper by Google Deepmind, University of British Columbia. And it was a real fascinating paper. And you know why I know this? Because I made a video more than a year ago exactly about Genie. And I explained in 38 minutes all the technical details of Genie. So now we use this kind of transformer. And if you don't remember, very short summary, we have here a very special ST And we have our temporal attention, our spatial attention, our classical feed-forward layer, and what we call here ST transformer architecture with spatio-temporal blocks. The rest you find in the video, beautiful. And then the second step is rather similar to N1 by NVIDIA. Because what we want to have an autoregressive world model with an action-aware pre-training. So step 1, the model conditions here, the prediction on the latent actions, enabling here some fine-grained frame-level control. But then we want to train here, of course, a diffusion model, because we want to have simply then the action vector added to a particular video frame, and then the diffusion model should be able to generate the next time step, the prediction in the future. So if I say I have an image of a hand coming closer to a pencil on a table, and I have then the action vector lift up from the table, then the next frame, video frame that should be generated is my hand holding now the pencil, 1 centimeter above the surface of the table. So this diffusion model, this diffusion-based latent diffusion framework is here now with our latent action and should provide here this high-quality prediction. So it should be able to transfer here this action, lifting up a pencil between the different video frames, should understand here the abstraction of the action to make it transferable. Easy, I know, I told you it's going to be an easy video. Core standard variational autoencoder. A little recap, if you're not really sure, what is it? This is here what we're trying to maximize. This is our Kullback-Leibler divergence. If you're not absolutely sure, we have here not the standard variational autoencoder objective, because remember, if our Kullback-Leibler divergence constraint was too tight, the latent codes was lacking here this richness that we were looking for. And if it was too relaxed, then we had here a problem with generalization ability. So you remember, we introduced here this beta hyperparameter. And then, as you see here, the second term, so beta equal 1, this is identical to the standard variational autoencoder. Beta greater than 1, it's a stronger regularization effect, and less than 1, the reconstruction term was emphasized. So careful how you define your beta for your system. Now, if you want to learn more about this is a paper that I used here for my deeper understanding, and I would like to recommend this to you. I know you look at this and say, who are those persons? I don't care. I just look at the paper and I think, hey, can I learn something from this? Is this in a way, written in a way that I say, hey, this is fascinating. This looks absolutely interesting. Rational autoencoders, Kullback-Leibler divergence. They explain here this in some beautiful details. And what I like, especially our visualizations where you have a neural network, where you have a little bit of a physical potential, and then you have a real detailed mathematical deduction, and then you arrive exactly at the equation that we are using in our code. So I like this kind of paper, where I really try to understand what is happening, why we are using this formula, why we are coding those equations then, C++, Python, whatever you go with, PyTorch. This is a paper I like, and I would like to recommend this paper. But in general, coming back, we do have a very easy two-step procedure that you know from the last video on N1 by NVIDIA AI. So, easiest one here from the paper, latent action autoencoder. So we have here a frame at a time t, and then we have here a frame at a time t plus 1. And you see here, if we go just for a video game, this person or object, whatever it is, just jumped. So the action for us is clear as human. The latent action encoder, that the action type is jump up in the air or whatever. So we encode this now in a mathematical space, in our latent action space with a particular representation. So we have now this vector r tilde, this is now our jump vector. And if we then have that we take here the image here at a time t, and we add now this jump vector, and with the latent action decoder, it now generates here an image, t plus 1, where the person is now midair, it's jumping. Great. And we have a continuous latent action. In the second step, you notice, This is now where we say, okay, we have a diffusion model, so we have a diffusion loss, but never mind. Again, we use here our latent action encoder. So we extracted a latent action from the video using here in step 1, the latent action encoder, this one here. And by leveraging here the extracted action as a unified condition, we pre-train now a world model, here our autoregressive world model, that can perform autoregressive rollouts at inference. So if we have trained this enough, then when it's inference time, and I come here with my frame at a particular time, and I understand my historical frames, and I have my latent autoencoder, this world model now immediately understands that what is the next frame, what is the next prediction if I have a latent action like jump up in the air. So you see, rather easy. Training model is clear, inference behavior is clear. That's it. Yeah, let's have a look at the study. I told you here, it's called AdaWorld, Learning Adaptable World Models with Latent Actions. It's from March 24, 2025. And it's a beautiful study. As you can see here, we have here a PhD student in its third year at Hong Kong University of Science and Technology, and the other one are here from Harvard University, Google, Deepmind, University of Massachusetts, MIT-IBM, and everything else. So what we have in essence, we have with this model, we can transfer now latent actions from one context to diverse other scenarios without additional training because we have the diffusion model. We have for this particular paper here a beautiful GitHub repo. You see, I'm a little bit early. It's really just published here. You see, this one was just built 1 hour ago. This was built 5 hours ago, 7 hours ago. But you have the code, you have the model, real nice. So if you go there, it has only 17 stars. Maybe you like this idea. You have here the code and everything available for you, free GitHub, and we have an Apache 2 license. Great. What I also like here in this particular video, you have some information about the person. So you often ask me, hey, can I get in contact with you about this paper? I'm not the author of all those papers that I present to you. What I do, I just go there, maybe it's a GitHub, you know, and I see, okay, PhD student at Hong Kong University since fall of 2022. You have here all the contact data, you have here the model card, you see what the person already published, or you go simply to Google Scholar, you look here at the other authors, at the co-authors, you understand exactly, I'm sorted here for the year, so 2024, 2023, 2023, I understand what the persons are working on, what they are doing, and you see here the co-authors. You see here their professional affiliation. If you click on them, you see their publication and everything. So I go there if I want to get in contact, if I want to have additional questions, if I have, I don't know, collaboration interest, you can use those instruments, contact them directly. A lot of researchers are really happy if you contact them, if you ask about their work. So I have never encountered any problem. Everybody was helpful, trying here to explain their work, and great corporations. Let's come to an end, and I want to have a very particular ending today because, you know, I just like to reflect on this a little bit. And you remember in this particular videos where I said, did OpenAI betray us all? Because I realized here at minute 19 in my video that all those human-generated data set and then there's all this internet copy data set, and then the synthetic instruction following data set, and then the synthetic chain of thought reasoning data set, and the Monte Carlo tree search algorithm for multiple branches, and the new graph topology for complex nonlinear reasoning data set. And then in this video, I showed you the first part here. We all came back here to a minimum set here that is just required to have here the perfect logical chain for causal reasoning. And I said, why do we have to take this detour? Why could we not just go from a human-generated data set more than 5 years ago, think about what we are doing, analyze that we do not need to copy the whole internet, but we just can go just to the perfect solution. And I wasted more than 5 years going here, this detour. And now I arrived here for the language optimization, again at a minimal set here of logical chain conditions. And reasoning chains. I now said maybe we don't have to do the same now if we do this video understanding now. No? So maybe we don't have to build hundreds of new data centers. Maybe we don't have to train here the World Foundation model on all of YouTube or all of social media. And maybe this time we can choose a more intelligent approach, not just more is more and more of the same, but maybe we start to think about which model we're gonna apply. So there you have it, a very short overview here. World Foundation model, the new AI revolution if you want. LLMs were yesterday just a tiny part now of the World Foundation model. AI now really wants to understand here the complete world, everything happening, texture, temperature, pressure, touch, sensitivity, everything, understand why we think in a way. Now some global corporations say, okay, we just copy here the complete content of social media. I don't know if social media is really the perfect training data set for a deeper logical understanding, but it is available and some will do this. But I think maybe if we use our brain a little bit more, I think this was nice. Harvard, Deepmind, MIT, IBM, Hong Kong University, a beautiful cooperation about how to advance the World Foundation model. And if you're interested in this next revolution of AI, why not subscribe? And I see you in my next video.